Eric, we only heard the last part of that question. Could you just repeat the very first part?
Describe the timing and environment of this alluvial fan and when it occurred.
Well, as you might guess, Eric, we don't have an easy way to get really absolute dates on Mars independent of the crater impacting record. And if you have a very small surface, the uncertainties go way up in your estimate of that. The somewhat longer answer is that this is one of the things that we really want to do with the mission, is because that alluvial fan and the time equivalent deposit that's downhill of it, where you can let your imagination guess what might be there, we want to know whether or not that package will then run under Mount Sharp and actually be the older thing that we have discovered or investigated. And the other hypothesis is that it is the younger deposit, and we expect it to abut and onlap the mound, go like this against the mound. And we'll see a geometric relationship. We really won't get into that question until we've driven to what we call this mound skirting units, the very base of the mound. And that's going to be a big part of this mapping exercise that we're doing right now, is to try to find the key places where we could go to see whether it does this or whether it does that. And so we might be waiting a year to get to that part of the mission. However, if you take it in sort of the way that it presents itself right now, most simply, you could guess that it would be younger. And in that case, what's cool about Mount Sharp is that it takes us from the time in Mars's history right down at the base of Mount Sharp where we have clays to the time when we have sulfates. And then maybe 700-800 meters above it, we cross a boundary. And everything up there, its morphologic character, the physical stratigraphy, the mineralogy, suggests that it represents the dry period of Mars. And I, for lack of a better contextualizing phrase, I like to refer to this as the Great Desiccation Event of Mars. This is the thing that everybody's been wondering about. How did Mars go from being a wet planet to a dry planet? And we hope to cross that boundary and get at that. But as you know, if you draw an analogy to the way we study the Earth, we have things like the Great Oxidation Event. It turns out, and initially we think it's a single unidirectional trend. But then it turns out, as you do more research, you see, well, there's precursor events and there's events that happen after. And I think a lot of people now think that there was a phase in Mars's history in Amazonian time when it may have been wet. And it just wasn't wet for a long period of time, and maybe Gale Crater has just captured one of those younger pulses. And the amazing thing about it is that we may get to investigate this broad range of environments in Mars's history. But TBD on the actual stratigraphic relationship.
Okay, we have another question actually in the row right in front.
Hi, Irene Klotz with Reuters. I have a couple logistics questions and then a science question. Do you, and I know this might be for the next panel, but do you know yet if another trajectory correction maneuver is going to be needed?
It may not, but we should wait for the next panel to answer that.
Okay. And for John, if the checkout and everything goes as planned, when do you expect science operations to begin?
It's sort of as you're guessing already. I mean, it's kind of a fuzzy progression. We land and we start checking things out, but the important thing to remember is every time we check out a science instrument, we're making a measurement, and so when we turn them on, first thing we do an aliveness test, and then after that we do a health and safety test. And in the course of doing most of those tests, we actually acquire data that comes back down to Earth that gives us some sense of what's going on. But until, we'll do that for about the first, 12, 14 sols, roughly. The first 2 weeks will be spent putting up the mast, using the instruments that are associated with the mast, doing remote sensing. And then after that, we have a little break in the action we call intermission, where we're going to be able to drive for the first time. So when we do the second part of checkout, when we want to put the arm out, for example, we'd like to put the arm out on something we think is interesting. So we might drive a couple of meters, a few tens of meters, and along the way, we're going to do some more characterization of the cameras. We're going to do some characterization of the ChemCam. We're going to turn SAM on for the first time and do a sniff of the atmosphere. And that's an engineering checkout, but it's a science measurement at the same time. And so then after that, we'll, a few weeks after that, we'll be doing the contact science instruments, and somewhere between a month and 2 months after we've started, I would guess we will have collected the first soil sample and maybe even drilled the first rock, roughly. So it'll be staged in sort of days, weeks, and months until we're really ready to go and we get the keys to the rover.
Thanks. And I guess another kind of big picture science question. You mentioned the SAM instrument. Will the rover have anything that's going to be able to characterize any atmospheric methane? And if so, would there be any way to distinguish whether it's geologic or biologic?
That would be the tunable laser spectrometer, which is part of the SAM package. And it's during the intermission, we're hopeful to be able to make a measurement when we do the instrument checkout. However, again, just to condition expectation, that measurement will not be long enough to give a definitive answer to the yay or nay question about methane in the atmosphere. We need a longer period of time to do that, so that will wait till slightly longer in the mission. And in the event that we detect methane, what we can do is determine the isotope ratio of the carbon that's present in that methane. And even if it turns out that it's very light, which is often what's associated with methane on Earth that's of biogenic origin, there are abiotic sources that also produce methane. So we'll always be in this somewhat equivocal situation of saying, it might be or it might not. But the first thing is to just ask, is there methane in the atmosphere or not? That's what we're trying to do.
Okay, and Irene, your first question gave me a perfect opportunity to remind everybody that we do have, this is the first of 2 news conferences this morning. At 11 a.m. Pacific, 2 p.m. Eastern, we will have our mission overview engineering news conference, and any questions about entry, descent, and landing will be addressed there. But in the meantime, I believe we have more questions here for our science panel. Let's go ahead in the first row.
Yeah, hi, this is John Russell with Reuters. When I told my wife that I was coming up here, the first thing she wants to know is, when are we going to put somebody on Mars? And so the perception is, how big a step is this in that process? And then secondly, how excited are you guys, about what's going on?
Part of the design of the Mars Science Laboratory was, in fact, to create a capability to get a metric ton to the surface of Mars. And hopefully we've done that. And that is going to help us go in a long way of understanding how to get to the surface of Mars safely with large payloads. I think also as background and some necessary steps, we need to make measurements at Mars to understand the planet, not only in terms of the science, but what it can tell us in terms of what would be the safest way to get to Mars and have humans go there and explore. And RAD is a great example of one of the things that we're doing that's going to help the science, but also will greatly inform what we need to do for future human explorers.
To go back to the putting someone on the moon, how big a step is as far as being able to do this job from back then to doing what we're doing now? Because there's a perception when you talk to people about exploration that nothing has changed since then. We've been stalled, but I'm just wondering from you guys how wrong that perception is.
Well, one of the things to keep in mind is actually sending a robot to go and basically make your measurements is a difficult thing to do. We have a hard time doing that here on this planet, much less sending it to Mars. And we have another major issue with sending humans, sending them to the moon compared to sending to Mars. We have a very different radiation environment, and we have a travel time that's a big issue. I mean, Mars Science Laboratory is taking 8.5 months to get to Mars. To the moon is a 3-day trip. And that makes a huge difference in terms of, something went wrong, let's go home, versus, sorry, guys. So there's a lot that goes into it, and then you fold in, because of transit time, how much more stuff you have to take with you. You have to get back. So we're not stalled at all, and I think we've made tremendous progress in certainly getting robotic effectors to do our job so we don't have to send humans right away. And we can learn a lot of background information and find out if there are ways we can go to Mars and actually use the resources there to make the whole trip a little more cost effective.
Okay, I think we have a few more questions. Let's get a mic over here to the... Yeah, go ahead. John?
John Johnson. Speaking of the habitability issue on the trip to Mars, what would that big spike have done to a human crew?
Well, so John, the spike inside the rover was observed by RAD would be sort of the environment that an astronaut would experience, and I think the spike in and of itself isn't lethal. Not that size of a spike. It would have to be a much larger spike to have short-term risk from that one particular event. But when you consider a long-term mission to Mars, we're talking 2 to 3 years round trip. It's all cumulative. So it's the background galactic radiation environment as well as the numbers of those spikes as they add up over time and the size of them, and then what sort of shielding you can provide on the surface as well.
Well, given that, then, what have you learned about the potential for a human crew to survive on the trip?
Well, so far there's 3 parts. There's the cruise out, there's the one way out, there's the surface time on Mars, and then there's the cruise back. Cruise back, we would hope, would be similar to the cruise out, although you can't really predict those the solar storms or the solar particle events. But what we've learned is that the contribution to an astronaut's total lifetime dose limit, which NASA has established, it's a non-trivial fraction of it. It's a significant fraction. We're still analyzing those and reducing those data, to get the exact numbers. But it's a significant contribution to an astronaut's career limit for radiation.
Okay, we have time for a couple more questions. Let's go to the second row here. All right, that's fine. Go ahead. We'll get to you, too. We'll just go in the order the mic appears. Yeah. Okay, go ahead. You
want me to go ahead? Okay.
Yes. Sorry about that.
Okay. One question each for the 2 mics. Mike Malin, describe the advancement in data storage, image storage that you've got with MSL compared with Spirit and Opportunity.
Okay. These cameras are significantly more advanced than the Spirit and Opportunity cameras, though they are probably not as advanced as something you have in your pocket. The cameras have larger detectors, and the storage, we have the equivalent of an 8 gigabyte card in the camera, so we can store in the camera without having to rely on the rover to store it in its memory. Each camera has an 8 gigabyte memory, and so the total cameras have 32 gigabytes, which is a fairly large amount. I'm not sure if it's the largest amount that's ever flown in a NASA spacecraft, but it's probably pretty close.
All right, I think we had a question. Oh, I'm sorry, Craig, did you have a follow-up?
Yeah, I had a follow-up. A broader question for Mike Meyer would be in the context of the 21st century, in terms of laying a true, highly detailed database on Mars. Kind of wax eloquently, if you would, there on just how significant MSL will be, no matter what future missions are selected when.
Yeah, the Mars Science Laboratory was conceived more than 8 years ago, and it was recognized. We actually went through several committees looking at what was needed to be done to have an astrobiology go to Mars. And essentially, for the first couple of tries, the answer back was, we really can't do that. We don't have the resources. That's a little too advanced. And we finally came to MSL and the opportunity to select the instruments. And these are fantastic. This is the first roving analytical laboratory we've sent to any planet. And it is a laboratory. It's amazing that we can do chemistry and we can do mineralogy there on the surface. And in many ways, any geologist would die to have something like this with them when they're out in the field. So It is a tremendous asset, and the degree of engineering that goes into making this rover to last the whole Mars year, and